In this video, we will be talking about Hess's law. Some reactions have changes in enthalpy that are very difficult to measure. Maybe the reactions take place very slowly, or maybe they occur in multiple steps. And even when we are unable to measure enthalpy change directly, we can sometimes calculate it based on the enthalpy changes we know for other reactions. Change in enthalpy is a state function, which means that the total enthalpy change for a chemical reaction doesn't depend on the pathway it takes. It only depends on the initial and final states, where it starts and where it ends. Getting from reactants to products can occur in one step or even two or three or more. However, the enthalpy change will remain the same regardless of the path. In this diagram, we see an exothermic reaction that has two proposed pathways. It doesn't matter which path you take. The change in enthalpy will be the same for both. Which brings us to Hess's law. Hess's law states that if a process can be written as the sum of several stepwise processes, the enthalpy change of the total process equals the sum of the enthalpy changes of the various steps. We used Hess's law before when we were looking at standard enthalpies of formation and using those to determine the change in enthalpy for a reaction. The reason we could add up enthalpies of formation of the different compounds in order to get an overall enthalpy for the reaction is Hess's law. Consider the chemical equation: 4 moles of ammonia plus 5 moles of oxygen yields 4 moles of nitrogen monoxide and 6 moles of water. To find the change in enthalpy, we can look up the heats of formation from a table. This equation states that the enthalpy of reaction is going to be the sum of the heat of formation of the products minus the sum of the heat of formation of the reactants. We're going to plug in our numbers and we're going to solve, and we get negative 1170.22 kilojoules. Now, what we just did using our equation was, in a way, taking a shortcut. Let's look more closely at what is happening in our reaction. First, the reactants break down into their elemental states, and then they reform into the products. The standard enthalpies of formation we look up in tables are the enthalpies needed to form molecules from elements in their standard state. Why does this equation have a minus sign in front of the reactants? Well, the minus sign is to turn the standard enthalpies of formation for the reactants negative. Think about it. Breaking down molecules into their atoms is the opposite of forming molecules. We're running the formation reactions backwards, and when we do, we need to flip the signs on our table enthalpies, and that minus sign in the equation flips them for us. Let's use Hess's law to calculate the enthalpy of a reaction. Say there's a reaction we want to know the change in enthalpy for, but that we don't have enthalpy of formation data for. Maybe we don't have a calorimeter, or the product doesn't last very long. You should remember from previous units that if you have reactions that occur in multiple steps, the equations for these steps can be balanced with respect to each other and added up to make an overall equation. The reason we can do this is because of Hess's law. It doesn't matter if the reaction is 1 step, 2 steps, 3 steps, or more. All that matters as far as energy and enthalpy are concerned is where the reaction starts and where it ends. Hence, we can use Hess's law to help us find the enthalpy of an unknown reaction using the enthalpies of reactions we do know the enthalpies of. In other words, we can algebraically manipulate equations with known enthalpies, so they add up to the equation we want to know the enthalpy of. This works for enthalpy of formation equations as well as regular equations that aren't enthalpy of formation equations. But when we do any of this, there are rules we need to follow. The first one has to do with scaling and multiplying equations. If you multiply the number of moles of a reaction, the value of the enthalpy change must also be multiplied by the same amount. Delta H is directly proportional to the quantities of reactants or products. If you double the amount of reactants and products, the enthalpy change of the reaction will also double. The second rule has to do with what happens when you flip an equation. Sometimes when you're trying to add equations for steps, you need the equation to be in a particular direction so that you can cancel out intermediates. But what if you only know the enthalpy change for a reaction that runs in the opposite direction? For example, maybe you need to know delta H for A plus B yields C, but you only know delta H for C breaks down into B plus A. Well, we can flip an entire reaction, but only if we change delta H to the opposite sign. In other words, the enthalpy change for a reaction in one direction is equal in magnitude but opposite in sign to the enthalpy change for the forward reaction. We can see this in these two reactions here. Notice that when we take the top reaction and we reverse it, the sign of delta H also reverses. It becomes the opposite. However, the changes in enthalpy are still the same magnitude. They are just opposite in sign. Let's see some examples of Hess's law in action. Iron 3 chloride is formed by the two-step process outlined below. We want to find the standard enthalpy of formation for iron 3 chloride, which we don't know, based on enthalpy of formation reactions that we do know. So here is the formation reaction for iron 3 chloride, and we don't know the heat of formation for this one, but we do know the ones for these two. And notice, we have an intermediate. Now, if we were to add these two equations, we would be able to cross out our intermediate. Well, conveniently, these equations add up to our overall equation. And because of Hess's law, we can add up their enthalpies to get the overall enthalpy of our reaction. Negative 399.5 kilojoules per mole. Now let's look at a slightly more complicated example. Calculate the change in enthalpy for this process. Now, notice that unlike in our previous example, we're not using an enthalpy of formation reaction here. We know this because we have 2 moles of product. Well, we're going to use this information, these two equations here, that we do know the change in enthalpy for. Now notice that the nitrogen monoxide is an intermediate and that we can cancel this out to get our overall equation. But in order to do this and make sure that everything is balanced, we must first multiply the entire second equation, including delta H, by 2. And once we do, our equations add up to the final equation we want, and our changes in enthalpy also add up to the enthalpy of our reaction, which in this case is negative 66.4 kilojoules. Okay, now let's get into some Hess's law gymnastics. We are asked to find the change in enthalpy for this reaction here based on these 3 reactions. So where do we start? Well, the first thing I like to do is to backtrack. I want to take a look at my overall reaction, and then I want to identify the compounds that make it up and see where those compounds are in the 3 equations I need to add. And so when we do this here, we can easily see where these terms are and what we're going to need to do to them to get them into the right place. So when we look at equation 1, we see that fluorine, molecular fluorine, is on the product side, but it needs to be a reactant. So we need to flip this equation, and when we do, we need to flip the sign on delta H as well. And so our sign will now turn positive. The second reaction looks okay, but we need to flip reaction 3, since the chlorine trifluoride needs to be on the product side. We also need to flip the sign on delta H when we reverse this reaction. So it turns from a positive to a negative. Now, let's look at our three revised reactions again. We see that we have two intermediates and a catalyst, and all of these need to be canceled out. If we were to multiply equation 3 and its delta H by 2, this would do the trick. And so let's go ahead and do that. And now our equations are balanced with respect to each other, and we can cross out our catalysts and cross out our intermediates and add everything up, and we get this equation here. Notice that this is double what our original equation was, so we want to make sure we get back to our original equation, and in this case we're going to have to divide everything by 2. And our change in enthalpy for the reaction is negative 104.5 kilojoules. In summary, chemical and physical processes can often be represented as a sequence of steps, and the enthalpies can often be added to obtain the enthalpy for the overall reaction. When a reaction is reversed, the enthalpy change stays constant in magnitude but becomes reversed in mathematical sign. When two or more reactions are added to obtain an overall reaction, the individual enthalpy changes for each reaction are added to obtain the net enthalpy of the overall reaction.